So we're going to continue on talking about LTI systems. In particular, this lecture is going to focus in on thinking about the development that we've had with these unit kicks. In other words, the Dirac delta function, and how important this object is in terms of thinking about linear time invariant systems. So in fact, what we're going to do is broaden the discussion a bit to talk about just the general concept of singularity functions. So we're going to revisit the delta function and talk about things like, when I think about a delta function, we've called it a delta function, even though really it's defined only in terms of an integral quantity. But what is the derivative of that delta function? What's the integral of that delta function? What is the second derivative? These are concepts that we normally think about with any function that we might work with. And what does it mean now with these very special functions that we are now building all of our architectures for LTI around, right? Which is, if I kick the system, what's the fundamental response? So this delta function now is playing this huge role in terms of anything I want to construct. And so we want to understand a little bit more in depth what these singularity functions are like. So if you remember, here is the definition, let's say x of t convolved with the delta function. Remember, the convolution operator is just simply given by this integral, but now what we had in there before was a function h when we were typically looking at this for constructing solutions, but now we put the delta function in there. And what we know about the delta function, it just simply sifts out the value when tau is equal to t. So in other words, we've already written down the solution. So the delta function, when you convolve with it, it only pulls out the value that matters at x of t. In other words, when the argument here is 0, when t is equal to tau. Okay, so that is a definition that we have. This is just follows straight from just whatever how we've defined a convolution, and and using the sifting properties of that delta function. So here's a question. So what if we take x of t in this formula right here and also make it a delta function? So now you have a delta function is equal to a convolution of a delta function with itself. So this is an interesting way to define a delta function. The way we defined a delta function previously, right, was we took the limit as delta went to 0 of a box that had width delta and height 1 over delta. But now here is a different way of representing this delta function. It's convolution with itself. And what does that look like? So this is a new singular function, right? Which is, we're going to call this object r of delta, which is the convolved version of it with itself. And it actually looks something like this. This is a different way to approximate that short pulse. What we did before was a squared up rectangle with width delta and height delta, but this is an equivalent way of doing it. Notice that now the base length is 2 delta, height 1 over delta, area under the curve is 1. And if you remember from several lectures ago, when we first introduced this delta function, I showed at least 4 different ways to represent the delta function, all which were valid limiting sequences for representing this object that we say is the fundamental kick to the solution, this delta function. And so, one of the questions is if we do this finite approximation to this delta function, what are the differences by using some of these different representations of the delta function? So this chart actually has some of this. So for instance, we might want to take an example here, some differential equation. Here it is, a pretty simple one. And then we ask the question, okay, when we kick this system, I'm going to use 4 different types of kicks. One, the kick is the delta function itself. Okay, so here's the kick to the system, x. And I'm going to kick it with a delta function. So what I'm looking for here is the h, right? If I kick this system here with a delta function, the response to that system gives me h, which is the fundamental response of the system. But now I'm going to show you in these charts different, what are somewhat, they're kind of qualitatively the same, but they're quantitatively different. So what I'm showing you here is, this is as a function of delta getting smaller and smaller. So as delta is 0.25, 0.1, 0.025. In other words, remember, we're going to take this delta going to 0 limit. And in this first chart here, you can see, as I take delta going to 0, it gets squeezed into here. But notice it has this sharp structure, and that's if the delta function is given by our standard delta, which is delta here, which is a box of width delta and height 1 over delta. But I just showed you an alternative way to write down a delta function, which is here. Delta convolved with delta. Here are the solutions for this. Now this is when x of t, this is this r of delta I just showed you, which is that tent looking function. As again you squeeze delta to be smaller, it looks qualitatively similar, but notice you have a little bit different structure to that solution. Let's go on 4 more. And this here is delta convolved with r. Here's a different way of representing this, and this is r convolved with r. This is this representation. So all 4 of these, in the limit as delta goes to 0, are identical. But notice for finite delta, they look a little bit different. So it's important to understand, I've just given you here 4 different ways to represent the delta function, right? In these different configurations, all which are delta functions convolved with each other. So this is an interesting property about these delta functions. There's more than one way to represent this kind of idea of a short kick, finite duration, unit area under the curve. 4 different ways to do it. They all kind of look similar. And in fact, in the limit as delta goes to 0, they all collapse to exactly this. Okay? So this is your fundamental response. But remember, part of a lot of the signal processing that we're doing is this is, in some sense, an idealization. Often you can't solve the system exactly, so you're going to approximate it, and so you're going to have to make decisions about how exactly you want to approximate it. And I've just given you 4 ways to do the approximation, right? So for instance, in the first way, you just use the delta function. Notice the cusp that forms here. You might want something smoother. You might want something that has continuous derivatives. So you might move over to this representation instead. And notice as you do the convolution, notice how it kind of flattens this thing out, right? So it's this time response takes it quite a while to actually come over that curve and down versus this is pretty sharp. It's way over here. So anyway, these are choices you make in your signal processing operations about the kind of properties you might want to see in your response functions. So this gets us to this idea of, we can now think about manipulating this delta function. And so we're going to start thinking about concepts like, what does it mean to take a derivative of this delta function? What does it mean to integrate this delta function? We've already actually talked about integrating the delta function, and it gave us the unit response, which was 0 and then 1. So that's established, but let's talk about this more broadly. So the unit doublet. So here what we're looking at is a function that essentially gives back the derivative of x. So in other words, I put in the signal x, what comes out is its derivative, okay? So another way to say that is, what I'm looking for from a signal processing point of view is I'm putting in a signal x, I want to ask the question, what do I have to multiply this by? Let's call it u1t, so that it produces the derivative. In other words, the response is to produce the derivative of this function. Okay? All right. So how do we start thinking about calculating that? Well, the unit doublet is really thinking about u1t. This is what our object that we're trying to look at is the fundamental derivative response. In other words, u1t, when you kick the system, right, it produces a derivative. Let's call u2t the fundamental response that produces a second derivative. So in other words, I'm looking at some operation here. I'm looking at what is this u2t that when I hit it against x of t in a convolution gives me back the second derivative. What does u1t have to be so that when I convolve it with x of t gives me back the derivative? So you see what we're going after here is we're actually going after saying, I want to sift out, I am sifting this out at the current value, dx dt at t, but not the current value. I'm sifting the current value as derivative or its second derivative. What do these functions have to look like to do this? And so now we start getting into this idea, and by the way, second derivative, somehow, this convolution, we just talked about the fact that in LTI systems, right, we have this ability to do associative and properties and so forth. This which produces a second derivative, ut2, u2t, is basically a convolution with u1t against u1t. Okay, so that's one derivative, second derivative, and that should be the same here. So the question is, in fact, you can do this k times. So if I have k of these, somehow what it should produce for me is the kth derivative. Okay, so what do these fundamental blocks look like? Because what we're really going after here then is, from a sifting point of view, I want to sift out first derivative, second derivative. I want to sift out different properties of a function. And now it's derivative functions. And so I need to understand what that u1t is to get that. Because each u1t will pull out a derivative estimate. So let's start to construct this u1t. And here's one way to do it. Again, there's many definitions of a delta function, so we're going to use the simplest one, which is the one we kind of learned early on, which is delta t, delta here. It's not a sorority. You have to have one more delta for a sorority, I think delta, but this is just two deltas. And so what this is, right, is to take the derivative of a function, which is that box. It's a box of with delta, height 1 over delta. And if you take the derivative of it, it's basically looking at the difference, which is delta t minus delta over delta. So this is the difference. So this is the definition of a derivative, right? So this delta t is just take the difference, divide by delta, take the limit as delta goes to 0. And so when you think about doing that, now you take this x of t and multiplying by this, notice what happens. This function here, which is now composed of two delta functions, and you're going to squeeze them together, this one here is going to pull out the value of x of t, right? It's going to sift that value. And this one here is going to sift the value at t minus delta, which is there, divided by delta. But by the way, isn't that the definition of dx dt? It is. And so you see right away, just using this idea of a derivative, the definition of a derivative, it already tells you something important. So if I want to look at this delta function derivative, it's sifting out the derivative. It's composed of two delta functions, one in the positive direction, one in the negative direction. Let me show you a picture of it. This is it. So this is the derivative of the delta function, right? So the delta function is a spike that goes to infinity, 0 everywhere. And the way we make sense of this, right, and again, is sort of in this integral way. And so this is what the derivative of the delta function is. It's a spike to infinity here, spike to infinity there. And what are we going to do? We're going to take delta goes to 0. So these spikes are going to go to negative infinity and positive infinity. And this distance between them is going to go to 0. So it's going to be two spikes, one positive and negative. This is called a dipole. Okay? So essentially in some limit, you're going to have a spike to infinity this way and a spike to this way. This is often called a dipole. Okay? So that is this object that sifts out not the function, but the derivative of the function, because in fact what it does, it sifts out this difference right there. Okay? So that's kind of interesting. So we're working with these singular functions, and we have to manipulate them in creative ways because these aren't continuous objects. And so we use these ideas of constructing some representation of the delta function and taking limits, and then we can get these dipole type structures. Let's go the opposite way. So u1 was an object that I multiply xt by to produce a derivative. And now what we're going to talk about is u minus 1. So u1 is going to be differentiation. U minus 1 is going to be integration. So this is going to be the unit integrator. So what we're looking at here is u of t is, you just integrate over a delta function. This is sort of like your unit integrator. So you took the delta function and you produced the integral of the delta function, okay, which is the step function. Now we already had done this, and so essentially what we're looking at here is, well, if I have some function y of t, x of t integrated against this unit step, I actually get this, the integration of x, which is sort of your unit step function, right back out. And so if I wanted to integrate twice, I would just convolve u minus 1 and u minus 1. And that's u minus 2. So you see that u minus 2 is integrating 2 steps over the delta function. The first step is, of course, the simple step function u of t, but you can continue this process and develop a concept of a u minus 2, which is integrate that twice, okay? This, in fact, gives you something simple, which is you integrate it twice, you get t u to the t. And if you integrate it again, now you're going to get t squared, u of t, and so forth. So now you have a concept of a unit integrator, right, in terms of these baseline singular functions, and you also have a differentiator in terms of these unit singular functions. So, by the way, this is written now in the convolution form, so you can just write this all out. These are just simple integrals in many ways. X of t composed against, or convoluted against u of minus 2t is essentially x of t convoluted against u of t twice. Okay, and u of t now is, you could put it u minus 1, but u of minus 1 is just, it's just a step function. And so here's the first one times u of t, and then you do it a second time, and this is what you get, 2 integrals, essentially. Okay, so you can do these integrals out and represent all of this in some formal way to get out the solution. So you first integrate up here to tau, then you integrate tau to t. Okay, so that's the way to represent, sort of in some sense, these unit integrators. And just like the unit differentiators, if you do this k times, you can just convolve them with each other k times to produce u of minus kt. Now, what you're actually going to do then is some big integral here, right? You're going to integral among, one integral nested in another integral and nested in another integral to do this all out. Okay? So these are representations then that are generic. They're using this idea of singular functions, which are basically your delta function and your unit step, and being able to construct a wide variety of operations that can produce derivatives and integrals for you very nicely, okay? So the kth derivative response, u of k, is just a convolution using the fundamental response u of 1, right, which we showed you was that dipole. And the kth integral response is just, you're going to integrate in some convolved way, right, this integral k times over the unit step. Okay, neither this integral nor computing these dipoles is that very difficult to do. And what we want to define then is these basic unit operations. So, we're doing everything here in terms of u of k and u of minus k, but the basic operation is u0 is the delta function. And if I go u1, it's the derivative of the delta function. U minus 1 is the integral of the delta function. Of course, the integral of the delta function is easy to work out. It's just u of t. The derivative of this is that dipole. And if I integrate this one more time, it's t ut, and so forth. So you get a whole cascade, but these are your 2 building blocks right there. And if you want to think about it, the building blocks most important is the delta function. This is what we're working with throughout the course. And so the ability to work with this delta function becomes really important for us. And by the way, this is where it becomes interesting. Notice that the delta functions that we have been working with are this rectangle of width delta, height 1 over delta. But you could easily show that if you worked with a Gaussian, in fact, I showed you a Gaussian integral when we first introduced the idea of the distribution several lectures ago, that you could say, I don't want to work with that rectangle, I'll work with a Gaussian, which has unit area under the curve, and I'm going to squeeze that Gaussian down. Then it's super easy to actually define the derivative of the delta function, the second derivative of the delta function, because you're just integrating that Gaussian, or differentiating that Gaussian. So just keep that in mind, okay? There are lots of ways to represent these singular functions. We're just working with one, but the derivatives of the singular function and its integral of the singular functions are definitely things we want to do, because they're going to sift out for us instead of just sifting the solution out, I might want to sift the first derivative or the second derivative, and this is how you're going to do it. More than that, these operations are inverses of each other. So u minus 1, which is an integration step, u1 is a differentiation step, and they basically undo each other to give you back to where you were. Okay? Back to u0. More generally, if I have k steps and p steps, my overall convolved piece is u of k plus p. So these could be, 2 and 3, or it could be 2 and minus 3, which would give you minus 1 here. So this is a nice representation. You can hit it with integration and differentiate alternatively. And remember, integration and differentiation are just inverses of each other. So if you differentiate something to undo it, you just integrate it, and vice versa. And this is basically all this is saying right here is exactly that fact. But remember, everything starts here with this basic function. And so if you want to develop methods where you can say, what I want to be able to do with my system is pull out, use the system and sift out values of the derivative or second derivative, it's very easy to do with these kind of functional architectures where you're actually multiplying it by the derivative of the delta function or second derivative of the delta function. Again, I want to make this comment. All of this sits under the aegis of what's called distribution theory, which is a broader framing mathematically of how we handle all these singular functions. And we handle all of them in terms of integral forms. So the integral becomes super important for us because that's how all these functions, which are 0 everywhere and infinity at one point, we handle all of that by saying, well, it all makes sense in the context of being able to represent this in an integral which sifts out values. So if you want to learn more about that, this is the kind of Google search term you would use, which is distribution theory. And there's quite a bit of work there because we've been using these delta functions for a long time. So that's going to be all I want to say about this. And this kind of finishes off a second chapter on LTI and Oppenheim and Willsky. But the reason we spent so much time talking about these delta functions is, again, for LTI systems, the main thing we want to do with them, continuous or discrete, kick the system with a delta function, see what the response is. That response that we have in the LTI system is now going to be the basics of reconstructing all solution forms. Because once we know how it responds to a fundamental kick, all of the solutions are a summation of that fundamental based upon where you kicked it in time. So just understand that it's a superposition of those fundamental kicks shifted potentially in time from where the kicks are happening. That's going to be the representation generically of any solution to our LTI system. Okay, so we're going to talk more about that as we go forward, but hopefully that closes off at least a lot of the basics for LTI systems.